Hey guys, good afternoon. So, oh yeah, in case you didn't know, I posted, oh, sorry. Okay, in case you didn't see, I posted assignment 2. Oh, I missed something in the chat. Hello, are you guys hearing me now? Okay. Okay, yep. Good afternoon. Okay, in case you didn't hear what I was saying, I was just saying that there's assignment 2, which has been posted to my e-learning. Okay. And for that, I wanted to do a few examples or something in Wednesday's class. So just try to take a look at a few of the questions if you have a chance before Wednesday. This assignment is 3 questions to be and due on Friday. So that's why I wanted to do some of them on Wednesday. So you can see what's going on. Okay, so what we want to do this week is finish talking about relations if we can. Okay, of course, it turns out all along a function was just a special kind of relation, and that's what we've been focusing on so far. But of course, relations, I mean, the more familiar example is like less than or equals, or membership, set membership, and things like that. Okay, so we want to talk about the different properties, especially equivalence relations, and also partial orders, things like that. Okay, just a moment. Okay, sorry about the interruption. Okay, so yeah, our plan, we want to get all the terminology we need for like basically equivalence relations and things like that. Okay, so on assignment 2 we'll see this, but I just wanted to at least mention it. So we have the power set. Oh no, sorry. We have something that's like an exponential. Okay. Definition. Let's take 2 sets A and B. Then we define B to the A to be the set of all functions f, such that f is a function from A to B. And remember, that means we can translate this. This means the domain of f is equal to A, and the range of f is a subset of B. Okay, and then we have like a proposition which says, as long as if A and B are sets, then B to the A is a set. Okay. And this notation b to the a kind of is just it turns out to be very illuminating. So let me just tell you a few examples. Okay. In fact, if A has n elements and B has m elements, then there are B to the A has m to the n elements. Okay. Actually, this is just like we'll see later how we can prove this rigorously. Okay, but just roughly, if we want to construct a function from A to B, and we have, you know, and so we go through each element of A and we choose an element of B for each element of A. So for the first element of A, we choose an element of B in m ways. For the second element, we choose the value of the function in m ways. We do that n times. Okay. Okay, so that's one way where, you know, the notation b to the a has a relation with the size of the number of functions from b to the a, but it also has another another kind of thing is that you know, another example. Okay, so we'll see later, one way to define the natural number 2 is just to be the unordered pair of 0 and 1. We'll see how that makes sense later. But this is our definition of 2. Then we can look at the set of all functions from this unordered pair to R. That's called R2. Okay, so let's look at this. Okay, each element of R2 is a function from 0, 1 to R. Okay. Well, there's you can see that a function from 0, 1 to R is basically a choice of one real number for f of 0 and another real number for f of 1. And we can put those two choices in a vector. Okay, we can put those choices in a vector. We kind of associate f with this vector f of 0, f of 1. And now this is regular R2. Okay, this is just regular R2 that you need in linear algebra. But you can think of a vector in R2 as a function from 0, 1 to R, which is like an element of the set R to the power 2. Okay, so right. Just to give you an idea of the different things that are going to happen later. Okay, so on the assignment, I think I've asked you to prove that B to the A is a set. So we might talk about that more on Wednesday. Okay, now there's one more definition of a function I want to make. Okay. So let S be a function. The domain of S is going to be I for index, and then such that S sub I, meaning the value of S at I, is a set for all the elements of the domain of S. Okay. The product of S is just denoted pi S, is defined by product of S is the set of all F's such that the domain of F is the same as the index set, and then also such that F of I is in SI, okay. As an example, to kind of see what's happening, we could set our set I to be 1, 2, 3, 4. S1 could be the set alpha beta. S2 could be the set of all real numbers. S3 could be just another set, I guess. Maybe the set of natural numbers. And S4 could be just a singleton. Oh, sorry, I've gone below. Okay. And so S is a function, 1, 2, 3, 4, from I to these 4 sets. And now, you know, if we put F1 to be alpha, F2 to be pi, F3 to be the number 4, and F4 to be 1, then this F is an element of the product. Okay. And there is and it is kind of like, it's very similar to just taking the Cartesian product of these 4 sets. It's like alpha beta cross R cross N cross the singleton 1. Okay. So using functions, we kind of get a way to define like really like complicated Cartesian products. Okay. Okay. Okay, so now we want to go back and we want to go through all the definitions we need to talk about kind of the important types of relations. Okay. Maybe you remember, you know, reflexive, transitive, and symmetric. Well, we have relations, so we need to define all those. We just need to like quickly remember all those definitions for all the different types of relations there are. Well, almost all. Actually, that's probably not true. Okay, so definition. Okay. Let R be a relation on A What does that mean? Let me just remind you. That means the field of A, and I'll remind you what that means too. The field is just the domain of A union, or sorry, R, the field of R. The field of R is just the domain of R union with the range of R. And the definition of being a relation on A just means that the domain union the range is a subset of A. Okay. Okay, then R is called reflexive if for all A in A is related to A. And okay, and just to reiterate here, you know, for functions, or for relations, you know, we define the relation first, and then we say a relation being reflexive. You have to specify what is it reflexive on. Okay, so you can't just talk about a relation being reflexive. You have to be talking about a relation on A, whatever A reflexive relation on the integers, but it's not a reflexive relation on the real numbers. So if R is reflexive or not kind of depends on what A is. Okay. Just notice R is reflexive, again, on A, if and only if the identity is contained in R, right? Because what's the identity relation on A? The identity relation on A is a set of all ordered pairs A comma A, where A is in A. Okay. So being reflexive means that A is always related to A, which means that this is always in R. That means that the identity relation is contained in R. Okay. Of course, we have reflexive. Well, what's next? Well, we have symmetric. Let R be a relation on A. R is called symmetric if for all A and B in A, if A is related to B, then B is related to A. Okay. And you can see again what happens. R is symmetric if and only if R inverse is contained in R. Right. Remember, whenever we have a relation R inverse is just a relation that you get by, okay, and R inverse is a subset of R. That means that, you know, the typical element of R inverse is going to be, you know, like B comma A, and then as long as A comma B is in R, then B comma A is also in R. So that's a symmetric relation. Okay, our example of, our kind of example that we have in mind, or one of the examples we have in mind for reflexive and symmetric relations. Now we also have we also want to say what it means to be anti-symmetric. Okay, definition. Again, R is a relation on A. Okay. R is called antisymmetric. If for all A and B, if A is related to B, B is related to A, then A equals B. And then roughly you can write this in terms of the relation R. You can say that all the things that are in R intersect R inverse. It's just, I guess you should say it's contained in the identity relation. Okay. And then we also have transitive. Again, R is a relation on A. R is called transitive if for all ABC, if A is related to B, and in terms of the relation R, you can say, you can write that like R composed with R is a subset of R. Okay, that's transitivity. Oh, sorry, I missed this comment.
So you was given an example. If A and B is in R, then B and A will be in R. I was just asking if A and B and A will also be in R inverse.
Okay, so I think that is talking about a symmetric relation. So let's do a just as an example, let's prove this. Just so just to be sure, kind of check ourselves, I guess. Okay, so let's do that. So let R be a relation on A, then R is symmetric if and only if R inverse is a subset of R. Okay. And let me just remind you of a few of the notations. If I say that ARB is in R, when I say that AR inverse B, that has the same, or sorry, I should write it different. I should write, that just means A is related to B. Okay. And so R inverse is just the set of ordered pairs B comma A such that AB is in R. Okay. So let us prove this kind of proof. let B comma A be an R inverse. In other words, B is related by R inverse to A. Now the definition of B being related to A by R inverse just says that A is related to B. Now, since R is symmetric, B is related to A. A just means B comma A is in R. Okay. Now, this B comma A was an arbitrary element of R inverse. So every element of R inverse is an element of R. So therefore, R inverse is a subset of R. We know that every element of R inverse is an ordered pair because R inverse is relation. Okay, so that proves that if R is symmetric, then R inverse is a subset of R. And now you just kind of go backwards to do the other way. Suppose A is related to B, and we need to show that B is related to A. Now, B is R inverse related to A just by definition of R inverse. Okay, in other words, this just means that B comma A is in R inverse. But that just means B is related to A. Okay, so therefore, if A is related to B, then B is related to A, and so R is symmetric. Okay. And okay, and so we have written our, the definition of symmetric. Maybe that just helps us unwrap what's going on with everything, I hope. Okay, and the other conditions I wrote down too, you can also check that they're equivalent to the normal definition that you're familiar with. Right, like you can check that R is transitive if and only if R composed with R is a subset of R. You can check that R is antisymmetric if R intersect R inverse is a subset of the identity relation. These don't really help you to understand better what antisymmetric and transitive is, but it does kind of help these symbols like the R inverse and identity relation and composition, how those symbols interact with relations. Okay. So if you feel like you have enough time, you can try proving one of these if you want. Okay. So now we have kind of all our familiar terms again, like antisymmetric, symmetric, transitive, reflexive. So now we can define equivalence relations in partial orders. First, let's do equivalence relations. Okay, the equivalence relations. What's so great about equivalence relations? Well, this is our main tool to construct kind of new mathematical structures. Like when we have the natural numbers, how do we relations? If we have the integers, we construct the rational numbers using equivalence relations, and on like that, so on. Yep. And many other things too. So we really need equivalent to dig into how they work. So first, let's just define them in case you don't remember. Let R be a relation on A. R is called an equivalence relation on A if R is reflexive, symmetric, and transitive. And this is all relative to A. So it's not really right to just talk about an equivalence relation. You have to be talking about an equivalence relation on A, whatever A is. Okay. So let us now just take a 5-minute break. And when we come back, we're trying to get through to the end of equivalence relations. So just brace yourselves for that. Okay. Thanks for staying so far. I hope to see you back after in 5 minutes.